based on rankings from the Semantic Scholar search engine. Today, we are really honored to have him here to talk on the decision-making side of machine learning, computational, inferential, and economic perspectives as part of the Banquet. Again, I mean, I would like to really take this opportunity also to thank Professor Chiranjeev Bhattacharya, who made this connection for us. And without much further ado, let us hear from Professor Jordan. Thank you.
Okay, thank you. Thank you. It's my real pleasure to join you. I want to thank all of the organizers and thank my ex-postdoc, Chiranjeev Bhattacharya, who was a wonderful presence in my laboratory about a decade ago in Berkeley. It's an unusual format to be giving a banquet talk in this way. I hope that someone somewhere is having a banquet or having at least a good dinner. I think perhaps the things I miss most about not coming to India is the food. I love Indian food and I would have enjoyed a banquet with all of you. So we'll do that some other time. So let me just jump in. I'm going to talk about decision-making in machine learning. It's not really been the focus, but I think it's really important that it become the focus, and I want to argue why. So let me just start with kind of a few perspectives on AI. I wrote an article a couple of years ago called Artificial Intelligence, the Revolution Hasn't Happened Yet. And the goal was to sort of think about when we use this phrase, artificial intelligence, really what do we mean? What should we mean? What do we mean for the future? I think that it's important to have this discussion about what our goals are. The original goal was that of people like John McCarthy in the 1950s. McCarthy was the one who coined this term, artificial intelligence. He had in mind an aspiration, a dream, if you will, that we could imitate humans and computers. And we all know what this dream is. It was an interesting dream because computers had just become available widely, or starting to become available. And they had hardware and software. It kind of looked like the mind and the brain. So we should think about how this is related to thought. How could we put thought in computers? I think it's still an interesting aspiration. It's a fascinating aspiration, but it's still an aspiration. It's not really what's happened in the last few decades. We really don't have thought in computers. It's not clear what exactly that would mean. And I'm not even sure it's the best goal, given that our ideas are actually being used in real life a great deal out in the world in real life, large scale systems that impact people. We should be thinking about those systems and thinking about that impact less than our simple dream. In fact, if we were to build a thought in a computer right now, it's not really clear how we would use that, whether it would be good, whether it would be bad, whether we should build systems based on it, or just have it as kind of a toy, a thing to be looked at and played with. I think in the meantime, something else has actually happened, which is more impactful than thought in the computer. And it's really just using the computer to augment our own intelligence. Search engines are examples of this. They augment our ability to access information in the world, to remember things, to be creative, and so on and so forth. And this is continuing on. So the computer itself, in this case, is not having thought. It's not particularly intelligent. It's a big indexing system of some kind, or maybe a learning system. It organizes information in a way that we never had before. So it augments our own abilities. I think in the meantime, there's something else emerging, which is not classical AI, but it's not unrelated. It's what we might call an intelligent infrastructure, or maybe Internet of Things, if you will. It's the fact that our systems have become planetary scale. They're linked, and there's data flowing in these systems, and they're helping us to make decisions, and they're helping us to build systems that do things like commerce or transportation or medical care. And so that's actually what's happening, and we should focus more on that phenomenon. And what does it mean? It seems like there's kind of a new engineering field emerging, which has to do with planetary scale flows of data to help humans in all kinds of situations. What kind of systems are those? What properties do they have? Do they work? Do they fail? How could they be made safe and fair, and so on and so forth? So in fact, here's a little bit of my history of the more narrow field of machine learning. I really think it is the emergence of a new engineering field. And I think it's not just happened recently, and it's not just an academic phenomenon. It's mainly in the real world. So I think already in the 1990s, in the back end, at companies like Amazon.com, you had large-scale compute being used to run machine learning algorithms. They were usually random forests back then. And they were doing problems like supply chain management or fraud detection at huge scale. And you wouldn't have had e-commerce emerge if this hadn't happened. So there's a kind of $1 billion industry built on modeling things like supply chain. How long does it take to get products across the ocean? How do you build products so you can serve 1 billion products to hundreds of millions of people? That was not possible before. The second generation to me was the emergence of the realization that a lot of the data was about humans, not just about supply chains and things in the world. So it's about human preferences and human transactions and so on. So recommendation systems emerged in that era and changed the way that people interact with large-scale computing systems. Okay, I wouldn't necessarily call this AI at this point, but it certainly is machine learning, and it certainly had impact. The third generation is the one I think we're in now, I'm going to call this the pattern recognition era. It's the reemergence of neural nets. It's the same large-scale computing that was used in the 1990s already. It's just at a bigger scale, and it's data sources of the same kind, but at a bigger scale. But what's happened is the data is now not just about humans, it's data like speech data and vision data and translation. So it looks more like the classical AI dream of imitating a human. But I'd argue that it's not really imitating a human, it's just data analysis at large scale on interesting kinds of data that make it look like we're imitating humans. In some ways, we're faking the imitation of humans. But we're really just doing pattern recognition. And that's really critical because humans are not just pattern recognition systems. They're also decision-making systems. And that's what I want to talk about. And in fact, if you think about not a single human, but large networks of humans and networks of humans at planetary scale, interacting with computers, you really now think about a web of things. It's not just an intelligent agent, and it's not just a small collection of agents. It's a whole network. The agents aren't that important in some ways. It's the overall network that does things. And this starts to feel more like an economy, more like a market system, where the individual agent isn't so important. They just make a very localized, simple decision, but it's the overall web of decisions and the network that does intelligent things like bring food into a city or solve transportation problems or so on. And again, that's what we need to be thinking about, because that's how our systems are being used in the real world. Okay, so just to emphasize this again, the current era of machine learning is focused on pattern recognition. It's mainly been labeled data, finding patterns in data, and it's become a commodity, right? There are these software platforms that allow it to be used easily by large numbers of people, so it diffuses out in the world. I don't think pattern recognition is everything. It's certainly not thought in the computer, but it's useful, and it can be used for many, many problems. And industry is being created based on it, and that's all wonderful. That's great. But I think that it's important to understand that pattern recognition is not the same as decision making. The two are equally important, and especially when you start thinking about high stakes decisions, life and death decisions, when you start thinking about understanding decisions, about sequence of decisions, about simultaneous decisions, something that's been less of a focus in the machine learning community. And decisions when there are multiple decision makers and market in the context of particularly of markets where there's scarcity and competition. All right, so I'm going to be talking about these themes. I'll say a little bit more about decision making in learning systems, and then give some examples of research projects that we've been engaged in at Berkeley in my group that build on the thinking here about decision making at large scale systems. At the end of it, I do want to say something about some software platform that we've been building as well, because I do think it's important to make these things into a commodity that many, many people could use easily. And so we want to make systems that support decision-making, not simply pattern recognition. All right, so let me say a little bit more about decisions. So let's be really concrete about it. Let's imagine a situation where you go in to see your doctor, and you sit down and your doctor measures all kinds of things about your body. Not just the usual height and weight and blood pressure, but many things, including maybe your genome and all kinds of other data about your body, maybe 100,000 dimensional feature vector. And let's imagine that that's been put into a very large neural network that has been trained on all of the world's medical knowledge. Every piece of medical data in every hospital over time. So you might then ask, what happens in that situation? So the outputs of this neural network are going to be predictions about what's going to happen to you, perhaps. So maybe one of those outputs is interpreted as a kind of a heart disease output. And if that number is over 0.7, it's a prediction that you're about ready to have a heart attack. And now, so suppose your number is a little bit over 0.7, 0.701. Do you treat that number as a decision? Or you threshold it and you say, problem, is that a decision? And arguably, no, it's not a decision of any kind. First of all, you want to know about the error bars. You want to know, how sure are you that my number is over 0.7? Can give me some uncertainty estimate. And it shouldn't be just a Gaussian error bar or a bootstrap error bar. It should be something reflecting real uncertainty. Where did that data come from? How old is the data? What's the provenance of the data? Was it gathered on people like me? With what kind of machine? All those things contribute to an error bar, and they should be present in the error bar. I should be able to see their presence there. So it's really kind of database thinking, if you will, about things like relevance and provenance, but now done on statistical basis about the relevance and provenance for an uncertainty, okay? And you're going to have a dialogue about that, because new sources of uncertainty may emerge as you start to dig into the particular, your particular situation and your particular diagnosis. All right. Moreover, with a real doctor, you wouldn't simply agree that you're about ready to have a heart attack. You'd have a dialogue. You'd say, you do what if experiments in that moment. You'd say, what if I were to exercise more? Or what if, did you know another fact about me, that in my family we had a respiratory illness when I was a child? I had a respiratory illness, or so on and so forth. You'll think of new things that you never thought of before because the situation has changed. There's new relevance. And so in fact, now you realize that neural network didn't have all the world's medical knowledge in it. It can't. It can't have everything that's relevant to this given new decision that I'm making that I never had to make before. And that's always going to be true for consequential decisions. You're always going to kind of gather data in that moment. You're going to think about counterfactuals, things that weren't true but could have been true, and reason about them. That's what decision making is all about. It's not simply about thresholding a pattern recognition system. All right. Moreover, it's never about just one decision, okay? Even if a consequential decision. Today, I'm making many decisions, and they're at different time scales. And moreover, it's rarely about just me. It's about many people making decisions in linked ways. Other people's decisions affect me. In the context of the world medical system right now, treatment decisions for certain people lead to certain kinds of outcomes. We learn from that. The system learns from that. And other people have different treatment regimes. That's how a system evolves. Right now, it's being done in a very ad hoc way with very little kind of clear data analysis and provenance, and it's not really a system, but it should be if we were to have an effective response to things like a pandemic. Moreover, it's not simply sets of decisions across a network in a given moment, it's across time. And I don't just mean across a day or a few seconds, like in reinforcement learning paradigm. I mean across decades or years. A medical system works over years. So data that's 10 years old might still be good data. It kind of depends. And so that has to be taken into account. All right, moreover, finally, it really involves decisions, not just over a network over time, but also decisions that interact. So if there's scarcity and competition, which there always is in the real world for consequential real world things, that has to be taken into account, because I can't just make a decision and have exactly what I want. You do that in software, you don't do that in the real world. Okay, so let's be concrete again. Let's do a little thought experiment and think about recommendation systems. These are pattern recognition systems. They find patterns in existing data of, say, one person's purchases of books or movies, and recommend those patterns to other people, recommend them as decisions, but they're not really decisions. They're simply patterns, all right? And in fact, we realize there's a problem if we think about them as decisions, because in the real world, we will have congestion, we will have conflict, all right? So if you think about a system like Amazon that recommends the same movie to many, many people, maybe 100,000 people, because the network says they all like that kind of movie, that's not a problem, because you can copy the movie as much as you want. There's no scarcity. The same book you could recommend to many, many people. They could all buy it, and you could copy the book quickly nowadays. 10 years ago, maybe not so much, but now you can. But if you recommend the same restaurant to 10,000 people in some city, the size of, say, Mumbai, you're going to probably do that. If everyone's using the recommendation system, by Poisson statistics, there's a chance you'll recommend the same restaurant to 10,000 people. And that's a problem. You'll have created a line, and you'll have created a congestion. And how do you fix that? You don't fix that by simply kind of randomly choosing some people to get to go to the restaurant and other people not. That's not going to be transparent or fair. Moreover, some people might really care about going there, and other people might prefer a different restaurant, actually, if they think about it. And that's how a market works, where you start to have kind of utilities and some kind of notion of bids or preferences and matchings and things like that. Let the market decide who gets something and not have the computer decide. And I think this actually is where Silicon Valley and other IT companies actually kind of get it wrong. They're living in the virtual world of ad markets where there is no scarcity. They can do the same thing to many, many people. And they can also pretend they know a lot about you because they know your browsing history and they can decide what you want. And so if there's too many people being sent to the same restaurant, they might say, well, we know because of your browsing history what you really like, and we'll give you that. And I hope you kind of realize this is not a very intelligent thing to do, that humans are not so simple. A pattern recognition system alone is not going to know what restaurant they want in that moment. It's not going to know all of the relevant facts about that decision. All right, same thing about recommending streets to drivers. If you recommend the same street to many, many drivers, which you will probably do, you will create congestion. You could recommend the same stock purchase to many people if you have a stock recommendation system, which you just start to see now in companies, in countries say, like China. And if you recommend the same stock purchase to many, many people, 100,000 people are recommended to buy a stock, the stock price will go up artificially and you'll have destabilized the market. So these are all kind of little simple examples. You can think of many others. The point is you can't just have a standalone pattern recognition system making decisions. It's going to interact with other decisions and you will create things like congestion, instabilities, and very serious problems. So you have to think about that as you're building the system, not afterwards when you start to see the problems emerging. So the alternative way to think about this is you create a market and you use data to help create and structure the market. So that's going to be what's new here. Economists know how to create markets, but they rarely had data involved. They didn't have the preferences be unknown and learned as people are experiencing the outcomes. That's what's going to be new here. Machine learning brings in the data and the learning of preferences, and then the economic mechanisms kick into play and start to structure the way the overall system works. And I hope you can see there's a lot of research to be done there. How do you take something like a matching market and make it be a learning matching market? Or how do you take a bidding system or auction system and make it be a learning system that works over time and people start to experience things and change their preferences and make decisions accordingly, okay? So you could have on the one side, to return to our restaurant example, the way to think about that is not just a recommendation system. It's really a market where on one side you have diners who express a desire to have a dinner. On the other side, you have restaurants who have the capability of serving the dinner. And so it's a little bit more like, say, Uber or a transportation system. You have producers and consumers. They learn about each other because there are many, many of them. There's not just one or a small handful of matches. There's huge numbers. And so the learning system has to help with that. This is not new, this way of thinking, obviously, I hope. And David Blackwell is a good example of someone already in the 40s and 50s who was thinking about learning systems that were decision-oriented and not so much pattern-oriented. Blackwell was an economist and a statistician and a probabilist and many other things. So his approach blended these fields. And I think as time has gone on, we kind of lost the economics, and for a while, machine learning also lost the statistics. It thought of itself as a brand new field. Luckily, over time, we realized that many of the ideas were statistical, and we brought statistics back into, together with computer science to build machine learning. But we also need to bring the economics back because decision-making requires economic thinking. All right. So another way to think about this is that markets are really algorithms, okay? They're decentralized algorithms that do complex tasks. And even if you don't think about the learning side, you can think about markets as algorithms. So you can kind of blend computer science and economics. And this is the perspective of algorithmic game theory and other fields. And really what we're trying to do is to take algorithmic game theory and to make it more of a learning field, or machine learning is blended with it. All right, now I should say that markets are not perfect and markets have all kinds of problems, and they will have new problems as we start to make them more like learning markets. And so we will have to fix those problems and think about them and plan for them and all that. There needs to be research on this, and it's that those are opportunities. Markets have power, so you want to exploit that power, but that power creates problems, so you have to understand how to regulate that power. So just some examples at the interface of machine learning and economics are things like multi-way markets in which agents learn their preferences by exploration. So we have to really bring in exploration if we're going to do this decision-oriented perspective. We need large-scale multi-way markets where I have maybe not just 10 options, I have hundreds of thousands, like the number of restaurants in Mumbai, or some others, or even the number of books. I can't have experienced all of them. I've experienced a small subset. So maybe I need to be in a recommendation system where other people have experienced part of that subset. And the overall effect is that we learn about what's on the other side of the market, and we start to be able to help our decision making. And there's problems involving information sharing and auctions and so on. So the goal here is to discover principles, new economics and learning principles that allow you to build stable markets that work over long stretches of time, years or even decades, that adjust themselves. Our current learning systems don't work over long stretches of time. You gather some data, you find some patterns, they work for a little bit of time. The next day, things have shifted. You have so-called distribution shift. They probably don't work so well. And they certainly don't work over years. And so we have to work on this. All right, so let me give you now a very concrete project that we worked on at Berkeley to exemplify this style of research.
Professor Jordan,
this is work with my students Lydia Liu and Horia Mania. And it brings together one learning idea with one economics idea. The learning idea is going to be one of my favorite learning ideas, which is the bandit, the multi-armed bandit. Here's a picture of a multi-armed bandit. They allow you to think about learning in the simplest situation. You don't have a label, so it's not supervised, okay? And it's not unsupervised either. You get to have a reward, okay? So I might pick the first arm, and for each of the arms, there's an unknown reward distribution. And I'd like to find the arm that gives me perhaps the highest mean reward, or maybe not the mean, something else about the distribution, all right? So we want to think about doing this in the context of getting a reward, choosing something else. So we're really making decisions and we're getting rewards, and we're trying to observe something about the reward distributions. Now, we don't want to model the entire distribution. That's too much. We want to find the maximum. So we want to model aspects of the distribution. But if you just take the maximum so far, or you take the current mean reward for all the arms, that won't work. And so over time, people realized you have to actually bring statistics into the picture. So one of the algorithms that has proved successful, both in theory and in practice, is the upper confidence bound algorithm, where you model a confidence bound on the mean reward, okay? And so in this case, now arm number 2 has a confidence bound that has the highest upper confidence bound. Now, why is that a good idea? Well, why is an upper bound, a confidence interval upper bound, a good thing to use? Well, you might have it be high because you have the overall distribution shifted to the right. You have a high overall reward. So you should pick that arm because it has high reward, and you'll exploit the arm. You will get high rewards. The other reason that the upper confidence might be high is that you're very uncertain. So you should pick that arm because you're uncertain about it, and you should get more certainty about whether it's a good arm or a bad arm. So there's 2 reasons to pick the upper confidence bound, and the algorithm kind of blends those into one idea. So you pick maybe in this case arm 2, and you get the reward. And now the confidence bound will probably shrink, and you will either maybe pick that reward more if it shrunk and went up to the right, or pick it less if it kind of shrunk and went to the left. And you can now prove things about this algorithm, that in particular it has logarithmic regret. Regret is how well you do relative to someone who knew the best arm a priori in the beginning. They're just going to keep picking that arm. And you want to pick that arm eventually, but you need to explore the other arms. And if you didn't have any learning, you would have linear regret. You just keep having some regret on every trial. But if you have something sublinear like logarithm, that's a sign of learning. All right, so on the economic side, again, one of my favorite ideas is the kind of the simplest economics idea is a matching market. So here, there's no learning. This is just a market in which you have participants with preferences. So the buyers have preferences over the suppliers, and the suppliers have preferences over the buyers. And those preferences are assumed known to the algorithm and to the buyers and suppliers. So again, they're not learning anything. All right, and now the problem is to find a matching, to find a connection between buyers and sellers which in some sense gives everybody one of their preferred matches. All right, and so a famous algorithm in 1962 led to Nobel Prize was the Gale-Shapley algorithm, which kind of iteratively and tentatively makes proposals on both sides of the market, and they're accepted and rejected, and leads towards a stable match. All right, so our problem then is going to put these two together. What if the participants in a matching market don't know their preferences, but they have to explore to learn something about what things they prefer, and then we want matchings on the basis of those learned preferences, okay? So we're gonna have a regret notion of some kind, but it's a regret relative to a matching, which involves other participants in a market situation. So how do we do the mathematics of this? What kind of results can we expect? And can we get real algorithms that might work in real life? All right, so here we have a little thought experiment. We have two competing agents, and they're gonna pick the arms independently of each other. And occasionally they're both going to pick the same arm. And when they do that, we have to make a decision. What are we going to do there? The arms also have preferences back on the agent side of the market. So let's suppose that arm 2 prefers the bear to the human. Now, we don't know that a priori. Of course, the agents don't know that, but they learn here that the bear got it when there was a conflict. So the human says, oh, I realize that even though I like arm 2, the bear also likes arm 2. So I may not get arm 2 when I want it. So I better explore the other arms more than I otherwise would to account for that fact. All right, so I will have to have in some sense a higher regret because of the presence of the other agent in the market than I would have otherwise. All right, so we have a bandit market where we have these noisy rewards, and we have a congestion notion, which for us is that only one agent gets the reward if both of them choose it. And so now you have to define a new notion of regret that's kind of an economic regret. And I don't want to get into too much detail here, but it's kind of an obvious one, which is that assume you knew the preferences a priori, and assume that that oracle that knows the preferences gave them to a Gale-Shapley algorithm. It formed the optimal match, and then everybody picked their optimal choice. All right, that would give you a baseline, and then you define regret relative to that. All right, so the question is, can we learn in this situation? What kind of regret can we get? All right, so we analyzed we've analyzed several algorithms. Here's an example. We call it Gale-Shapley upper confidence bound. And it's simply that each agent has upper confidence bounds on each of the arms. And those upper confidence bounds are given to a Gale-Shapley algorithm, which returns a tentative matching. And then people experience the arm that they're matched to. All right, so we were able to prove a regret bound for this algorithm. And here it is. It turned out it's logarithmic. Okay, so we were able to prove that this overall algorithm can learn in this market, and in fact learn very well. Logarithmic regret is optimal. Moreover, we have a term in the denominator there, delta squared, which I could show you the expression for it. It's the reward gap between one agent and other agents. So if other agents have a small reward gap relative to you, that means you have some overlap, and you're probably going to have to explore more than you otherwise would, and that term will make the regret larger. And so we are taking into account the effect of being in a market for one's regret. Notably, however, it does not change the logarithm. You still have logarithmic learning in this system. Okay, having done that line of research, we started to use UCB ideas more widely than they'd been used before. And in fact, somewhat surprisingly, UCB had not been used in reinforcement learning. So reinforcement learning is, in some sense, the temporal extension of the bandit problem. But reinforcement learning is rarely studied with exploration in mind. It's just an optimization system, an optimal control system, kind of surprisingly. So there's not so much analysis of, there's not analysis of expected reward, but not so much analysis of regret in reinforcement learning. It's not entirely true, but it's partially true. So anyway, we decided we would study, UCB in the context of reinforcement learning. So this work with colleagues Chi-Jen, Zheyan Zhu, and Sebastian Bubeck. So let me not spend much time on reinforcement learning. It's not my focus here, but hopefully you all know that it's a Markov decision process where I have a state in addition to an action and a reward. And you may know that there's a debate in the literature about model-based and model-free reinforcement learning. In the model-based paradigm, you use your experiences to build a model of the state transitions, and then you put that into an algorithm that is a dynamic programming sort of algorithm that finds the optimal actions or policy based on the model. The alternative is to do something more like a Bandit algorithm, simply try things out and adjust the policy directly based on the rewards. And there's an argument about which is best, both in practice and in theory. And I'm going to focus on the theory side of the argument. So we have added now a UCB to the Q-learning algorithm. So I'm, again, not getting into details here, but if you know Q-learning, you'll see line 2, that's Q-learning in blue. And we've added an upper confidence bound to the Q values. That's the B sub T there. And there's an expression for B sub T down below. It's this extra little bonus that you get by using it a UCB. Okay, so we're now incentivizing exploration in the context of Q-learning. And the question is, can we analyze a regret here? Does Q-learning learn quickly when it has to explore in this way, or not so quickly? So I'm just going to summarize on one page sort of a large number of theoretical papers on model-based and model-free reinforcement learning using regret as our analysis. All right, so the top part is papers on model-based algorithms. And so if you look in the regret column, the third column there, you'll see that the regret scales as square root of T, where T is the number of trials, okay, number of episodes. All right, so that's not logarithmic, but it's still sublinear, it's square root. So that's good. And so it's viewed as the model-based, this is a success for the model-based paradigm. It can learn with square root of T regret. All right, what about the model-free paradigm? Well, if we go down to the second part of the table, you see Q-learning with epsilon greedy. This was the state of the art. It's to not use UCB, but use an algorithm that simply randomly occasionally would choose a different action than the maximal Q value. All right, so it's called epsilon greedy. And that did not have a square root of T regret. It had a T regret, pretty bad. And there was an attempt to do a little bit better. There was got down to T to the 4/5. Anyway, in this paper, we were able to use Q-learning with UCB and able to show a regret bound that it turned out to be also square root of T. So model-free is actually as good in theory as model-based from this point of view of regret when you add exploration into both of the paradigms. Okay, so I could go on about UCB and related ideas, things like Thompson sampling. But it's really of interest to add those kind of ideas, not just into reinforcement learning, but into all kinds of decision-making problems. So I'm going to briefly say something about another multiple decision-making problem that isn't just a single agent making decisions over time, like reinforcement learning, but rather it's a whole bunch of decisions being made in as a collection, okay? So this is going to be what's called the false discovery rate paradigm in statistics. This is not studied so much in machine learning. I think that's a problem. So I want to emphasize in this section partly why we want to study multiple decision making and not simply supervised learning and reinforcement learning. There's this other paradigm which is important. So again, people at Berkeley have worked with me here, Tiana Zernich and Aditya Ramdas. All right, so think about making decisions over a lifetime, and they can be asynchronous, there can be groups of decisions. And what I want to do is think about trying to keep the overall error rate on all of the decisions I've made to be controlled. I have small errors over all the decisions I've made. All right, so imagine that I'm working on some problems in a company, and I have a boss who kind of comes into my office occasionally and says, how many decisions have you made so far? My job is to test out various decisions, and I'm doing it with data. So this might be like at a hedge fund where you're testing out various possible, bidding patterns on stocks or ways to game them, to play the market. And so you test them out and you sort of see if they seem like they're likely to be a good decision or not. And so your boss will come in from time to time and say, well, how many decisions have you made so far? And you say, I've made 45. And the boss can say, well, what fraction of those are likely to be good decisions? And you want to be able to say more than 95% at that moment of all my decisions. And it should be the case that when the boss comes in next year and asks you the same question, how many decisions have you made up until now in your job? And you say, well, 5,000 decisions. And the boss will say, well, what fraction of them are good decisions? You should be able to say more than 95%. And the boss should be able to stop you at any time in your whole career and ask you, and you should have the overall error rate always under 5%. All right, so is that even possible? All right, it seems like errors will eventually accumulate and you can't keep them under some fixed value, right? But that's not the right way to think. It actually is possible. And there's an economics way of thinking about this problem that makes it clear that this is possible. And we have an algorithm that can do this. Okay, so we're going to talk about error rates that have an economic interpretation. We're going to be using ideas that from statistics called false discovery rates. So just very briefly, let's think about multiple decision making in some generality. So here we have 9 decisions to make. And let's suppose that the ones in gray, P1, P7, P4, P9, and P8, these are ones which are null. There should be no discovery made here. In this case, you say, nope, there's no evidence that there's something interesting happening here. Whereas in 4 of the cases, 5, 6, 2, and 3, those are cases where the data say there's something interesting happening here. You should make a discovery, okay? You should reject the null, if you will, in that language. So we don't want to just think about one decision at a time or a sequence. We want to think about the overall set of decisions. And so some algorithm might make a discovery in 4 of the cases, and then 2 of the cases, those discoveries were actually wrong. So the overall performance of this algorithm is that 2 of its discoveries, there were 4 discoveries and 2 of them were false. So the error rate of this algorithm is 2 over 4. Okay, so this is called the false discovery proportion, this notion of error. It's the number of false discoveries or no discoveries. All right, and then to analyze and do theory on this, you take the expectation of that, and that's called the false discovery rate. So I want to, on one slide, give you a picture of why this is so different from usual machine learning error measures like accuracy or precision recall kind of, or sensitivity, specificity, and so on. So let's imagine you're at a company where you're running A/B tests. Those are decisions, right? A yes/no decision. And you're doing each one of them on data. And so 10,000 decisions. You might be deciding about the website. Should you have a green color or blue color on the website? Or should you change the size of some gadget or something? All right. And let's suppose that in reality that there are 9,900 of these decisions are actually null. In other words, there's not really anything happening. If I change the website from blue to green, it won't get more customers. And this is true of any mature engineering field or science, that most of the things you try out are actually not meaningful, not real. Okay, you should not make a change because all the easy changes have already been made in the past. People discovered, the basic right theory or the basic good website or whatever, and small changes are not going to give you any significant boost. So let's imagine in this case that 9,900 of these are no discovery should be made, and only in 100 of those cases is there something to discover. So let's imagine you now run an algorithm on these 10,000 A/B tests, and suppose it's some really fancy neural network that has a really good error rate. And so suppose that it's type 1 error rate, meaning whenever you should not make a discovery, you make a discovery. That's a type 1 error, a false positive. You imagine your number of false positives, your fraction is less than 0.05. All right, so if you apply that to your data, 9,900 times you will apply this algorithm and get a false discovery 5% of the time. So you'll get 495 false discoveries. So 495 divided by 9,900, that's 5%. So that's good. That's only 5% errors on those cases where you should not make a discovery. And imagine that your network is also very good for its power. Not great, but let's imagine its power is 0.8. So that's its sensitivity. So 80% of the time when you're supposed to make a discovery, you do make a discovery. So if you apply it to those 100 places where you should make a discovery, 80 times you make a discovery. So that's good. So again, the fractions are very good. 495 over 9,900 is good, and 80 over 100 is good. So our accuracy looks really good from the point of view of a classical accuracy measure. But what about the false discovery rate here, the false discovery proportion, right? Well, your boss comes into the room and says, how many discoveries did you make today? And you add up your false ones and your true ones. You don't know that they're false and true, but the Oracle does. And so you add up the total number of discoveries and it's 575. And the number of false ones it turns out to be 495. So your false discovery proportion is actually 495 out of 575. So it's terrible. Most of your discoveries are false. Of course, you don't know that, but you give all those discoveries to your boss and they go and use them, maybe making bets on the stock market or maybe changing the website. spending a lot of money and losing a lot of money because you really did a bad job. All right. And so hopefully this gives you some pause that it's really important to think about the right way to think about errors. And it's not classical accuracy or least squares error or things like that. You got to think about the overall decision-making system here. This is a terrible result. Okay, so now the question becomes, how do I do it if I want to control the false discovery proportion? All right, and there are ways to do this. In statistics, there's something called Binyamini-Hochberg procedure. It's a good algorithm, but it makes some very strong assumptions. It assumes that you have all of the data all at once. You have a big batch, and so you sort the statistics. You sort the p-values, if you will, and you then threshold the sorted values. So it's very limited to a batch setting. And so it won't solve the problem we were talking about earlier of, your boss comes in every, few weeks and asks you how you're doing. That's an online procedure. So we need to find, is there an online anytime procedure for this kind of error control? All right, and there is. We've developed one called SAFFRON. There's also others in the literature. There's one called LORD from Andre Montanari and colleagues at Stanford. And Dean Foster was one of the original developers of this. He's now at Amazon. But the basic idea of this, and I'm not going to spend time on details, is that you can make decisions on an anytime basis because the FDP is a ratio. So if we go back to the FDP here on this slide, remember the FDP is the number of false discoveries over the number of discoveries. Both of the numerator and the denominator are random variables. They depend on your behavior. So you can make this ratio small in two ways. One is you can make the numerator small. The other is you can make the denominator big. All right, making the numerator small is controlling the false positive rate. That's classical machine learning. Making the denominator big, that's new. All right, that's making your number of discoveries large while you make the numerator under control. Okay, and so a new algorithm is needed for that, and it's possible to do it. It's called the SAFFRON algorithm. And I'm going to give you a picture of kind of how it works and refer you to the paper for details. Basically, it's an economics idea. I give you a little bit of wealth in the beginning, and the wealth is measured in units of alpha. So I could have 0.05, your alpha rate, and you use that to make a decision. And if you make a no discovery on your first one, you accept the null hypothesis, you lose a little bit of wealth. Okay, so your alpha comes down a little bit to maybe 0.03, and then you do it again, and you keep losing wealth. But eventually you make a discovery, and now the denominator goes up, and I give you a little bit of wealth that you can invest in the future. Okay, so there's a way of thinking about this economically, that your wealth goes up and comes down, goes up and comes down as you make decisions. And you can do that in a way that controls the overall FDP over time at any time. All right, so hopefully you'll find that interesting. I'm going to actually skip this next section here. I think I want to get to the last part on our software platform ideas. But let me just say a little bit about what this section is about here. This is returning to the Bandits problem, but doing it in the context of Bayesian algorithms instead of the UCB algorithm. So a Bayesian algorithm is one that has a prior probability and then a posterior probability that's being updated on each of the decisions. So in the case of the multi-arm bandit, you have a posterior probability on the reward distribution for each of the arms at any given time. All right, and this is nice because you can use Bayesian machinery to update your beliefs instead of using confidence intervals. That means you can put in prior distributions, and you can also have hierarchical models that bring together a large number of decisions and so on. So this adds to my theme of having not just one decision maker, but large numbers of decision makers. If you go to this Thompson sampling approach. All right, now the problem with the Bayesian paradigm generally is that you have to run sampling algorithms, and they might be arbitrarily slow. And so, optimization seems to be faster, and that's more like in the spirit of the UCB algorithm. And what we were able to discover in this line of work with a number of colleagues at Berkeley is that there's a way to do a gradient-based sampling algorithm, i.e. a Langevin algorithm, and make it be fast enough so that it can converge quickly in the context of a bandit algorithm. Okay, so that's the basic idea. Again, I'm not going to get into this section of the talk, but just to say that Thompson sampling is the Bayesian approach to bandits. Upper confidence bound is the frequentist approach. Most of the theory has been on the frequentist side on the right there, where you get these regret bounds. But actually in practice, the Thompson sampling is widely used. And I think it's going forward going to be one of the easiest paradigms to work with. So we've done some basic theory of Thompson sampling, and I'm going to skip over the slides for doing that, just to say that we've got kind of a way to have new concentrations that give you fast convergence of a stochastic gradient version of Langevin here. And I'll refer you to the paper if you want to see how we did that. Okay, so we get a regret bound for Thompson sampling with Langevin. So kind of putting together sampling algorithms with bandits with regret. We're able to do that in this paper. Okay, so for my last little few minutes of the talk here, I want to turn to software platforms. So in addition to working on algorithms and theory, I like to work on distributed platforms because that's kind of the computing systems of the day. And I like to think about trying to make commodities, systems that real people can use for real problems so we can start to try these ideas out. But again, I'm focused on decision-making these days. And so I want to integrate decision-making with pattern recognition. So I want a platform that'll allow you to run things like, TensorFlow or PyTorch inside of an overall decision-making system. And so the decision-making system might be doing reinforcement learning, but really I want to think more broadly. It might be doing false discovery rates. It might be doing bandits or matching markets. I want a system that allows us to explore this. So we've been developing such a system at Berkeley with a variety of colleagues there. We call it Ray. It's now being widely used actually in industry and in academia. It's an open source project now with many hundreds of contributors. And I want to just say a little bit about what it is. So this is a platform which attempts to take all of the capabilities of a learning system and put them together. All right, so the current ecosystems have training, they have serving, they have streaming, and all of these, when you decide to build a distributed version of your system, so that it's not just running on one computer, but on many computers, people think about how to do that for each of these separate tasks. So there's distributed training like Horovod. There's distributed model serving like Clipper. There's distributed streaming like Flink, and so on and so forth. Distributed reinforcement learning. Ray is an attempt to build a single distributed system that provides an API so that all of these capabilities live as libraries on top of the distributed system. And this makes sense just because the distributed problem is about managing many processors, GPUs or CPUs on a network, managing processes, managing data flows, and so on. That really should be done once, and then provide an API for these machine learning capabilities on top. Right, the other way to think about what we're doing with Ray is that if you think about a modern programming language such as Python, why it is so successful is that it's both functional programming and object-oriented programming. Okay, so functional programming, is widely used for simple implementations. Object-oriented is needed for stateful kind of programming. The interesting issue is that historically, when people went to Hadoop and Spark and went to the MapReduce paradigm, so they could run large-scale, pattern recognition and indexing algorithms in Google and other places, they got rid of the object-oriented side and they just focused on functional programming. So MapReduce is functional programming, and you did that because if you're running on 10,000 computers. Keeping state around is really, really hard because some of the computers will come up, some of them will crash, and it's really, really hard. So they simplified by looking at functional programming. Ray says, no, it's time now to return to having both objects and functions in our programming, in our distributed language. So we want to run on huge numbers of computers or processors, hundreds of thousands, and we want to have both functions, which we call tasks, and objects, which we call actors, in one paradigm. All right. Here is an example of a Python program that someone else wrote that was doing hyperparameter search for a neural network. All right, it was written for a single processor, and it did its job. It was a good hyperparameter search algorithm. This person then wanted to run this now on 10,000 computers, and so they didn't want to have to rewrite all of the distributed programming themselves to do that. So they said, what if I try Ray here? And they added some code. That's the red parts that I just added. That is the way that you change this into a Ray program. So Ray just adds its Python API. So you add a few decorators to the code to make it into a Ray program. And then immediately, this program will run on any number of computers that you want. And so this person was able to do that with a small amount of change to the code. We now have a large number of libraries that run on top of Ray. Here's just some example of high throughput architectures, gradient-based algorithms, and various multi-agent and derivative-free search schemes. Underneath the hood, there's a lot of work going on in Ray. It's doing object store management, object management. It's using schedulers. It's having control over all the schedulers, and so on and so forth. So, a huge amount of work is going on beneath the hood so that the API can be really simple, and you can simply write Python code at top and have all the capabilities provided automatically without you having to think about the underlying distributed implementation. So there are many libraries now developed not only at our Berkeley group, but also third parties have been developing those that run on top of Ray. You'll recognize many of them. All of these are now running on top of Ray, and some of them are running in production at various companies. Let me give you one example. This is from China. If you're Chinese, you may recognize the app on the left there. So this is a app that runs in the hands of about 1 billion people per day. And so they're trying to adjust the app, online to make better and better decisions. And so, the usual machine learning, pipeline is that you featureize the data, you do some training, and then you serve the model back to the device. They were updating this model about once per day, huge volumes of data. And they spent about a year of engineering time to bring that 1 day of model training down to 1 hour. And that increased their click-through rate by 5%, a huge change in income. They then decided to work on Ray. They actually are doing open source development of Ray in a Chinese company, which is kind of unusual. But you'll see their code if you go to the GitHub site. And they simply implemented this in Ray instead, and they were able to bring it from 1 hour down to 5 minutes using the Ray platform. And so Ray is actually being used in production here at this company. Here is a plot of growth of Ray compared to Spark, which was also developed at Berkeley. It's the world's most widely used data analysis platform. And you can see the growth of Spark. It started in 2015. Ray's rate of growth is matching that of Spark. The number of contributors as of September was about nearly 400. It's growing rapidly all around the world. People on the GitHub site developing code for Ray. And there are more than 100 companies using Ray currently, including Goldman Sachs, Amazon, Ant Group, Microsoft, Intel, and so on. So let me conclude my talk. Ray is a distributed Python system. It's open source. You can participate in it yourself if you'd like to. We'd love to have more contributors to Ray. I think it is emerging as a standard platform for large-scale machine learning-based decision-making. I think it improves upon MapReduce and Paradigm, including Spark, which is very batch-oriented. Ray is very much online, asynchronous-oriented, so reflecting the modern decision-making perspective. It doesn't conflict with PyTorch or with TensorFlow. Those can be viewed as actors within the overall Ray paradigm. The pattern recognition part comes together with the decision-making part inside of Ray. They don't conflict at all. Okay, so let me stop the talk there. This is a slide I already had up earlier, but just to return to the overall themes of the talk, is that the overall era, the current era of machine learning has focused on pattern recognition. Great progress has been made there, but there's unfortunately a tendency to think that that's all there is to the problem. First of all, it's not all that there is to the classical AI problem. Even a single agent trying to be smart needs to think about its decision-making. And decision-making is not just thresholding a pattern recognition system. It's not just making predictions. It's a whole field of its own. But secondly, the classical AI perspective is too limited. We shouldn't be just thinking about making a smart agent that can do pattern recognition. We should be thinking about large collections of decision-making flows on networks over stretches of time and thinking about market mechanisms and decision-making in that context. And now we'll need more than just the classical pattern recognition and thresholding. We need to think about collections of decisions and market mechanisms as we go forward. So thank you very much. I'll be more than happy to have some questions and discussion I'll stop there.
Thank you, Professor Jordan. Thank you so much for the wonderful talk. I'm sure if we were in person, then we would have had a whole bunch of claps. But this is a virtual thing, so we just go ahead with the virtual claps, right? So let me very quickly field a few comments and questions, right? So in fact, I myself worked for the past 4 years in healthcare,
Yes,
and
madam.
the uh, the first few things that you mentioned, right, resonated so well. So oftentimes it's also about the metric that you choose in a healthcare situation, right? So basically, for example, in a pathology use case, we ended up saying that, hey, top one accuracy is so much, but we could then have some human involvement possibly to handle some of the situations you mentioned. Um,
Well, yeah, no, my perspective is that it's not just computers on the network making decisions. It's a mixture of humans and computers in a variety of kind of feedback loops and corrections and decision making. So I didn't emphasize, in some sense, the HCI side of this, if you will,
Right.
but that's very much part of it. And HCI, I think, is a good perspective, but it's also been pretty limited. It's kind of one human and one computer. It's kind of the classical perspective. And not much, data analysis going on in that loop. So I think that, again, opening this thing up to, well, I got really doctors interacting with patients and computers are all involved in that mix. And how do I put that all together to make, better and better decisions and have them documented, have them transparent, have them understandable, and so on and so forth. All those things, you need principles for that.
Right.
And so I like to use the metaphor just briefly of chemical engineering. So, in the 30s and 40s, this field emerged. Before that, there was just chemistry, right? There was a person sitting with a test tube, pouring them and trying to understand what's happening in the test tube. And people got a great understanding. They had quantum mechanics and fluid flow and, chemistry was all developed. But then going from that to building a whole factory where these things are flowing around in all kinds of directions and all things are being created, and humans are needed to help adjust it in the loop so that the factory works and doesn't explode and develops product. That's the transition we need to make. It's that we're not just one person with a computer that's smart and we make the human and the computer smarter and smarter. It's really thinking about the overall, literally planetary scale of something like medical care. Yes, thank you.
True. So Shaurya is asking, is it important to consider consistency of decisions coming from different ML systems also? Like, for example, we take a second opinion when we, in healthcare situations, right? So to reduce or eliminate chances of wrong diagnosis. So for ML-based decisions, will consistency across different systems also be a desired characteristic?
Yeah, no, consistency is really important. I used a little bit of database language, if you noticed in the talk. So something like provenance is not a word that a machine learning person normally uses. That's a database word. And consistency is also kind of a database word, if you will. And what part of my message here is those concepts need to be brought into machine learning, but the challenges are more than they were in the classical database world. In the classical database word, provenance just means kind of, where did the data come from, right? But here is the data relevant to my current decision, right? How much error was there in that data? How much did the situation change? Was a different machine used to gather the data? Was it different people? All those kind of things are coming into it. And similarly with consistency, your decision, your view of some, outbreak might be different from mine, well, because you're looking at different situation, different context, different data, and so on. So we may not need to worry too much about gluing our decisions together, but we might want to. And that's, again, a statistical thing together with a database thing. So the system should be able to manage that. There will always be inconsistencies if you're in a distributed, decentralized world. And so that is very much part of the perspective. Absolutely.
Right. Now linking it to FDR, right? The one that you mentioned. So how do you handle cases when FDR is may not be the best metric? For example, in healthcare, right? I think people care more for false negatives, so is the method that you explained is extensible to the other side as well?
Yeah. So first of all, I don't agree with that necessarily. It's just every problem is different.
That's true.
Right?
That's
and the right way to think about this is that not that Mike Jordan would say you should be using FDR. Mike Jordan is saying you should not just be using precision recall or specificity.
Absolutely.
You should not be just focusing on one kind of thing. So yes, there's absolutely something called false negative rate, right? Which is the fraction of false negatives you have among all the negatives that you had. Okay.
Yeah.
So all the times I did not make a discovery, which fraction of those were false? That's a totally well-defined quantity. It's the complement of what I said there. And yes, there absolutely are mechanisms for controlling that. But again, people in machine learning never worked on that problem, the false negative control.
Right.
But you can, absolutely. And there should be more papers about that. And then there's a trade-off. You should have a way to trade off FDP against FNR, so absolutely.
In the decision making, you also talked about producers and consumers, and then how either their individual optimization should be taken into care, but also the system is involved, right? When making recommendations. For example, a job portal making recommendations for a job, too many people being shown the recommendation for this job, but maybe the job portal makes money if all the jobs get filled, right? So there is
but I want to think about the bring down the portal. So if you think about Google or Facebook, the portal is all important. They're making the consumer is making no money, and the producer is making no money. The person who made the video makes no money, all right? And Google makes all the money, right? And why they did that is they created a false, market, this advertising market that has nothing to do with the person who made the video, and nothing to do with the person who's looking at the video, right? And so I want to get rid of the portals, So I want the portal to be just like in the case of, say, Uber or transportation system. It takes 5%. Right? Really, all the focus is on the producer and the consumer and how to link up the right producer with the right consumer so the overall system works well. And you're absolutely right. The portal's got to make a little bit of money, but I want the portal's job to be serving the producer and the consumer. And not just simply providing a free thing to the consumer and then creating a different market to make money.
Absolutely. Professor Chiranjeev is asking, do the results that you presented have any relevance to multi-criteria optimization? So if I have, say, different utilities, I may have to balance multiple criteria. And do any of the results presented here shed new light on Pareto optimality?
That word Pareto is an economics word, right? So, so I didn't focus on that so much I have worked on it, but multi-criteria. But kind of the point, if I gave another hour-long talk, I would certainly have that problem in there, because that's very much, if you're going to be economics oriented, you always have to agree that we're not going to all share the same optimization functional, and so we've got to think about how to deal with that. And that's what Pareto optimality is about. And, so also I've worked a bit on min-max optimization, right? Where there's two agents, one who wants to go up and the other wants to go down. And if you simply do gradient descent ascent in that situation, you don't get good answers. And so that's a situation where, classical simple machine learning ideas doesn't work, but, many people, my group and others have figured out new algorithms that do work in that situation, that are gradient based, that are not classical algorithms from microeconomics. They're new algorithms, but they are actually handling the fact that one agent wants to go up and the other agent wants to go down, and you don't want to get into conflicts and limit cycles. There are algorithms that will do that. And so, I haven't worked so much on Pareto optimality, but I have worked a bit on it. And I think there's many opportunities there. Take the latest, greatest ideas from stochastic gradient algorithm analysis, try to apply them to a multi-criterion objective, and I'm sure they will not work. And that's an opportunity for research. Right.
So Gautam is asking online FDP, right? So now, for example, hedge fund may like to apply the discoveries so far altogether. So do we need to assume these are independent? One does not affect the other?
Now, you don't have to assume. The classical theory of FDR, the original paper of Benjamin Hochberg in 95, assumed independent decisions.
Nice.
All right. And that's kind of allowed you to do the mathematics. But now we've had, 25 years and independence went away at some point. You don't have to assume independence. First of all, people went to martingale style proofs that got rid of some of the independence. And then eventually there was kind of the independence could be removed. There's ways of doing that. So we've kind of removed all the assumptions that were originally there. We removed independence. We also now allow overlap of the decisions. You might be making a decision. It doesn't happen instantaneously. It might take an hour for you to collect data and make your decision. In the meantime, I might have an overlapping decision on top of yours. So we have now papers on asynchronous overlapping decision-making that are not independent. Clearly they're not independent, they're overlapping and so on. So it requires extra work, but it doesn't become impossible all of a sudden. It just is a little harder, but it's doable.
Right, right, right. So I don't know if you have like 5 more minutes. There are a couple of
Sure.
more interesting
I'm in no
questions.
rush. Yeah.
Right.
Yeah.
Okay. Awesome. So Professor Kamal is asking, can we use economic principles to reduce inherent bias in a learning system? So I mean, a little, and if so, what is the state of the art? I mean, if you.
Okay, so I think when you use a word like bias, you can't be just allowed to assume we all know what it means, because we don't. All right. So there's a very narrow notion of bias from a statistics perspective, which is the difference between the expectation of an estimator and the true estimator. That you'd like to make small typically, but not always. Right. Even in statistics, you sometimes allow some bias. All right. But really, the broader notion of bias is really a social science one, almost a legal one, if you will. And it involves decisions. It involves on how you treat people in making decisions, and it involves collections of people, and so it totally involves economic principles. If I think I'm being biased against, I've got to sort of say, what's my utility? What would I have preferred instead of the answer I got? Right. And so, and that needs to be taken into account by the system. Fairness is another example of this. The whole notion of fairness is that you're somehow respect my utility. It's not just that you give everybody the same thing. That's not what people want, right? People want to be respected for what they like and want. And if you build systems that do that, that's more of an economics metaphor. You start to become more fair, but that alone is not solving the problem either. So words like bias and fairness are fantastically important to be clear on the wide scope of them. And I do believe there you absolutely have to have economics and trade-offs, and how much fairness versus how much time versus how much expense, and privacy is another example of this. Privacy is not just a single definition. It has to be privacy relative to a trade-off where you might be trading off other things about gains or losses of various kinds. So yes, the field, it's going to take, I think, a few decades. I'll be long gone and retired or whatever by the time this starts to be a textbook field. But when we eventually have kind of like a chemical engineering class, and we'll have it for this new field, that'll have all those topics in there: bias and fairness and decisions and time and provenance and reliability and robustness and all that. It's not going to happen this year. It's going to happen over some decades.
True. Yeah, I think overall in the talk, right, the best point that I liked is about combining RL with bandits, and that was pretty nice. So there in the matching bandits, again, I can imagine that there could be some roles for the agents as well. I mean, consumers versus producers, and then trying to take care in the RL process.
So I talked about bandits and matching, but RL was different, right? I had RL with UCB. You can certainly, there's a multi-agent RL field, right? And it kind of makes some contact with what I was talking about, but there are two sides to a market, and you can decide which side you want to focus on. Do I care more about the consumers or the producers? Who makes the most money? Who's preferred? And kind of, so classical matching markets actually choose to prefer one or the other. And then there's ways of making them both happy. Again, this is part of the overall field, just to think about those kind of things. And if you're doing it over time, you start to bring in more of the RL perspective. But I already think that matching and bandits alone, forget about RL, is already pretty rich. And I think actually most applications of RL I can think of, really, you don't need RL. You just bandits. And bandits with a covariate vector that captures some notion of state. And there's not enough research on contextual bandits. That's very practical. And so what about contextual bandits meets matching markets? That's completely open. Someone could start to work on that and do a whole line of work. That's a great topic right there. But also the work I told you about was matching markets meets bandits on a centralized platform. So I actually didn't do the decentralized version of matching markets with bandits. And that's because that's a harder problem.
Got it. I think that is more or less what we have. And thank you so much. Thank you so much for the talk. I think all of us enjoyed significantly. And again, if we were all in person, we would have had many follow-up questions and so on. I'm not sure when we can have your next 1 hour talk here. So and in person this time. So we would really love to have you in person at some point here.
Okay, well, thank you, Manish, for being a great host. I really appreciate it. Those were great questions. And again, I thank everybody for coming out in the evening or wherever you are. I do look forward to meeting all of you in person. So thanks very much.
Thank you, Professor Jordan. Thank you, folks. Thank you for attending and for all the awesome questions. This is the end of day 2 of Chords Comad. And see you tomorrow on the third day in the morning. Yep. Thank you. Okay. We'll
Okay,
stop here. Thank you. Bye-bye. Yes.
Thanks, everybody.